Okay, welcome to lecture here. So we're just going to finish talking about a couple of things from chapter 8, acids and bases, and then we're going to roll into organic. Again, the notes should be up there if you need it. Okay, so we pretty much kind of finished organic chemistry. Not organic chemistry, we finished acid-base chemistry, and we talked about buffers at the end last time, and I just want to cover a couple of things here just to make sure on that chapter before we call it a day on it. We did skip two sort of examples. And first off, though, a reminder that a buffer is a solution that resists changes in pH. And it's able to do that because, again, as we talked about, it's made up basically of a weak acid part and a conjugate base, or a weak base and conjugate acid. So again, as we talked about last time, both of those things are in the solution to begin with. So essentially what a buffer has is that it does have basically both of those things in the solution. You know, it's got the acid part, it's got the base part. And that means that when you do add acid to it, more acid, it will do a reaction with the base part of the buffer, and it basically will make actually more of the acid part. It will use up some of the base part of the buffer. And same sort of thing happens if you add base to your buffer. The base will react with the acid part of the buffer, and it will actually make more of the base part of the buffer and use up some of the acid part. So ultimately what happens in a buffer is it's able to really prevent the formation of free H plus ROH minus. So really what a buffer does is it stops the formation of free H plus ROH minus. And again, it's really those two things that would be introduced into the solution when you add an acid basically to it, or you add a base. And by preventing really either one of those things from really forming, what it does is it ultimately keeps the H plus concentration relatively constant. Wherever it's kind of started, it remains relatively constant, and it thus keeps the pH also relatively constant. So as we talked about last time, a couple important things about a buffer. It does have to be a weak acid or conjugate base, or a weak base and a conjugate acid. That's because the weak acid or weak base is really something that can set up an equilibrium, like we talked about in that equilibrium chapter, and ultimately allow both of those things to remain in the solution. You cannot have a buffer that's made up of a strong acid or strong base, because really it won't be able to set up that equilibrium and create both of those things in solution at the same time. Secondly, again, a buffer is not necessarily a neutral solution. You could have a buffer at any pH you want. The thing is, whatever pH it starts at, it basically will be able to maintain that pH in that solution, even again when you add acid or base to it. You really won't see big, giant jumps in pH like you will if you add acid or base to, say, something like water, which is not a buffer. You would see a pretty big jump in the pH. All right. So the last thing I really want to talk about was, what happens when we have a pH of a strong acid. So there's several strong acids that I think we talked about. Hydrochloric acid is a strong acid. Nitric acid is a strong acid. Sulfuric acid is a strong acid. Perchloric acid is a strong acid. Hydrobromic acid and hydriodic acid. These are all strong acids. And what it means is, for example, if you had something like, say, 0.01 molar HCl, when you would have that HCl in solution, it's going to 100% break apart into ions. Again, it's a strong acid, strong electrolyte. So basically 100% of what you would have would be on this side. And if we do know that the concentration of the entire thing is 0.01 molar, it is a 1-to-1 relationship between the H plus and the HCl. That means that the H plus concentration would be 0.01 molar. And that's really what we need to know to calculate the pH. So at that point, we really can go right into the pH equation and punch it in. And that would get us a pH of 2 in this particular case. So a lot of what we saw earlier dealt with just kind of generic concentrations given to you, where it said, hey, the H plus concentration is this, or the OH minus concentration is this. Sometimes they'll actually give you the formula of something that's a strong acid or even a strong base, like sodium hydroxide, potassium hydroxide. And in a strong base, like potassium hydroxide, when it would break apart, it would break apart into K plus and OH minus. And from that, you could get the OH minus, which means you could get the POH, and then you could get the pH. So sometimes they'll actually give you formulas. And for our class, if you are given a formula of an acid or a base and you're asked to calculate the pH, you could pretty much assume that it's going to be a strong acid or strong base because weak acids and weak bases are much, much more difficult to calculate, and we don't come across any of those in terms of calculating the pH. So again, sometimes they may not just give you, like we saw in this chapter, the kind of generic H plus or OH minus concentration. Sometimes they may just actually give you some formulas, and you just use the formulas to get those things and then go into either the pH or the POH equation. So looking at, for example, another example here, this again is perchloric acid, also a strong acid. So when that would break apart, it would break apart into H plus and ClO4 minus. Again, here, in terms of pH, it is the H plus that's the most important. So if we know that this is 0.025 molar, it's a 1-to-1 relationship between these two guys. And as we talked about with concentrations, the concentration of the H plus here would be 0.025. And that means, again, that's pretty much all you need to go into your pH, minus the log of 0.025. And that would get you a pH of 1.60, which is also acidic, which makes sense as this is an acid as well. So that was kind of the last thing I just want to talk about here in acid and bases. Again, sometimes they may not just kind of give you the generic version. They may give you, like I said, some type of formula. And the good news is in our class, it will probably be a strong acid or base. So you pretty much can use that to get either the H plus or the OH minus concentration, and that will allow you to get to your pH. Any questions on that there? Okay, so we are then going to move on to chapter 10 again. I believe we're skipping chapter 9, which is nuclear chemistry. So we're now going to roll into chapter 10, and that should be our start of organic chemistry. So the good news now is, I guess, for some people is pretty much no calculations. So this is all going to be memorizations and naming and stuff like that. So you won't even need your calculator. You'll still need it, obviously, for chapter 8 and stuff like that. But pretty much from here on out for the rest of the chapters, it's pretty much more memorization of names, some reactions, and those type of things. So a lot more of that, kind of a lot of drawing type of things as well, kind of like Lewis structures. You have to draw some formulas and stuff like that. All right, so let's get into organic chemistry. Organic chemistry is basically the study of carbon. It's your classic first sentence in every organic book is organic chemistry. It's the study of carbon and other elements. And really basic organic molecules basically consist of carbons, hydrogens, and again, sometimes we substitute things like oxygens, nitrogens on there, sometimes sulfurs as well. But the basic sort of setup for a lot of organic molecules, as we will see, is basically carbons attached to carbons. And attached to those carbons are really hydrogens. And like I said, as we go through, sometimes we take off some of those hydrogens, we replace them with other elements like oxygen, nitrogen, like I said, um, along the way. And what that gives us is some different sort of organic molecules. For the most part, we see organic things in a lot of substances in our life here, but the basic bonding is carbon to carbon, which is a non-polar bond, and also carbon to hydrogen, if you remember from electronegativity, also considered a non-polar bond. So organic molecules are usually, for the most part, non-polar. There are some that have polar parts to them, which allows them to interact with things like water. But the vast majority of organic compounds are those sort of non-polar guys. So organic compounds exist in discrete molecules, and they're usually much weaker intermolecular forces than sort of ionic compounds, and that's because of what I was just talking about. So since the majority of them are nonpolar molecules, they are, if you remember from our intermolecular forces, going to basically be using dispersion forces. And if you remember, dispersion forces are those really weak sort of forces that occur between nonpolar and nonpolar molecules. So we get these sort of weak interactions with nonpolar molecules or organic guys. And that's why a lot of organic molecules, for example, are gases at room temperature. A lot of the first ones, methane, propane, butane, there are a lot of gases. And that's very different than sodium chloride, which is held together by intramolecular forces, that electrostatic attraction between the positive cation and the negative anion, that attractive force between those two, which is a very, very strong attractive force that happens between them. So all organic compounds, again, like I said, basically consist of carbon and hydrogen. We do sometimes substitute out the hydrogen for other things. One very important thing to remember, especially in drawing a lot of these things, is our good friend carbon. It only makes 4 bonds. Yeah, so that's very, very important. Carbon wants to basically make 4 bonds. And that's sort of the basis of how you sort of draw a lot of these organic compounds, is that idea. And I say that because sometimes as people start drawing these things, they do get carried away. And before you know it, poor carbon has got like 4,000 bonds happening to it. People just keep drawing bonds on carbon. And, he ends up with a ton and ton of bonds. So one very important thing to keep in mind as we go through these chapters, especially the organic chapters here, only 4 bonds to carbon, and don't ever do any more than 4 bonds because it probably will be wrong in that particular case. Carbon can form double bonds, single bonds, and triple bonds with itself, as we can see here. Again, all this is really obeying the octet rule. So if we remember, everybody pretty much wants to get to that 8 valence electrons, except for hydrogen. Also a very important thing to remember here with organic molecules, again, only needs 2 electrons, basically 1 bond, and not to go over 2 there with hydrogen, also really important here. So these are all different types of organic molecules, as we'll talk about. This guy here has all single bonds. This is an organic molecule known as an alkane. Has all carbon-carbon single bonds. This is also carbon and hydrogen, but it has a double bond, and this is a group of organic molecules known as alkenes. And lastly here, also carbons and hydrogens, a group of organic molecules known as alkynes, because it has a triple bond. So sometimes we talk about functional groups, and what are functional groups? Functional groups are really the part of the organic molecule that sort of describes what type of organic molecule it is. So those are sometimes referred to as the functional group. And for alkanes, as we will see, it's basically carbon-carbon single bonds, alkenes a carbon-carbon double bond, and alkynes a carbon-carbon triple bond. Having those different types of bonds also gives some of these guys some different properties based on the single bond, double bond, or triple bond that they have. So here's methane, which is CH4, and that's the simplest organic molecule you could have. It's basically a carbon with 4 hydrogens attached to it. It's got that tetrahedral arrangement, and that is basically your simplest guy you could have there. Ethylene, which is also sometimes known as ethene, is that 2-carbon guy that we saw earlier. Looks something like this. And again, sometimes called ethene. And if you remember, this was an alkane, it ends in ane. This is an alkene, it ends in ene. And that pattern goes with naming of things. Typically, they are named very much from their functional group, and they have a similar type of name. Now, a lot of alkanes are straight chain, as you can see here. Straight chain alkane, like propane here, has 3 carbons all in a row. So it's carbons attached to carbons, hydrogens attached to those carbons. Sometimes, a couple of ends kind of come together and they make like a ring type structure here. And these are what are referred to as cycloalkanes. And they basically are our straight chain guy where basically the 2 carbons kind of come together. This makes a geometrical shape, as we will see, which sometimes looks like a triangle drawn in line structure there. Sometimes we do have ones that are branch chains, and a branch chain is much like a tree. There's like a main kind of source there, and then off of the main source there, kind of like branches, there's guys that are coming off of it as well. So I won't draw in all the hydrogens there, but this is sometimes what is referred to as a branch chain, where you have a main sort of run of carbons, and then off of that main run of carbons, you have a bunch of sort of branches basically coming off. Now, organic molecules also contain other compounds or elements, like I said, besides carbon and hydrogen. And again, substituting some of those guys out gives us some different functional groups and different organic molecules. And some common ones are, like I said, nitrogen and oxygen are very common members of organic compounds. Fluorine, chlorine, and bromine, some halogens get on there as well. So typically, the number of bonds plus the number of lone pairs equals 4. So there is sort of a common sort of arrangement that a lot of these organic molecules will sort of take in terms of their shape or the way that they sort of come together. And that's what this table shows here. Again, hydrogen always looks like this. So just like in Lewis structures, hydrogen's always got to be on the outside with just one single bond. Again, carbon, very common, 4 bonds to it. Nitrogen usually will have 3 bonds in a lone pair a lot of times. Oxygen, a lot of times, kind of the single bonded version of oxygen organic molecules, will have 2 bonds and 2 lone pairs. A lot of times, a very common oxygen bond is something like this, which is what we find in an alcohol. That's the functional group for an alcohol, this OH group. And then here, a halogen can kind of go on there at the end, where it basically has 1 bond is surrounded by 3 non-bonding electron pairs. So most common bonds between, say, carbon is carbon and oxygen, and really kind of 2 main sort of carbon-oxygen bonds develop. We have this carbon single bond, usually to like an OH group like we see here. And sometimes the carbon just directly double bonds to the oxygen. Again, to maintain the octet rule by making that extra bond, we kind of lose the hydrogen over here, as you can see. And that's also sort of a theme, when you make, every time you make a bond, you kind of lose a couple of hydrogens that were there before. And again, it's just so that people don't go over the octet rule and are able to maintain that octet rule. So when we talk about formulas, there's a few different types of formulas that we commonly see in organic compounds. One is the condensed structural formula. One is the structural expanded formula, and one's really the line formula. So just to kind of show you the difference between those, let me go back here. So this right here, where we kind of take something like propane and we kind of draw out everything, all the bonds to the hydrogens and everything like this. This is what is sometimes called the expanded structural formula, or just the expanded formula. So this is sometimes referred to as the expanded structural formula. And basically you're drawing out all the bonds that are there to the hydrogens. Sometimes we kind of reduce this down to more simple format where we don't really draw out the bonds to the hydrogens. And this is what is referred to as a condensed. And some people call this a condensed structural formula, but most people just call it a condensed formula. And some people call it structural formula because you include the kind of lines here. But most people call it just a condensed formula. And then the last one is basically a line structure. And that little kind of mountain range there does represent what I drew on the bottom. So when you draw something in line structure, you don't include any carbons or hydrogens in the structure. It's supposed to be kind of a clean structure, if you will. So whenever you see sort of an end to a line or where two lines come together, it is a carbon. And carbon, again, needs 4 bonds. So it's assumed that all the rest of the bonds that get each carbon to 4 are going to be hydrogens. So this carbon in the middle has 2 lines coming in, which means it should have 2 hydrogens. Carbon on the far left there has 1 line coming in, which means it should have 3 more hydrogens attached there, again, to give each of the carbons 4 bonds. So line structure, though, this is typically what it looks like. Again, you don't typically write the carbons. You don't write the hydrogens. You do write something if it's not one of those things. So, for example, if you had like Br up here, that would be 3 carbons and a Br basically attached. So again, if there's something at the end of the line that's typically not carbon, they do put it in. But if it is just carbon, you don't really write it. So sometimes you'll see this sort of zigzag formula, sometimes referred to, and it almost looks like mountain ranges, kind of drawing these things. And again, this is line structure, and each of these represents a carbon. So this would have 1, 2, 3, 4, 5, 6, 7 carbons. And again, each one needs to get the 4 bonds. So the guys at the end would have technically 3 hydrogens there. And each of the guys in the middle have 2 lines coming in. So each of the guys in the middle technically, again, have 2 hydrogens attached to each of them. And as you can see, why we don't typically draw all these in, it gets a little crowded there. So we kind of do that just typical line structure where we just kind of do the mountain range. We also see the zigzag structure because of the geometry. This is basically 1, 2, 3, 4 electron pairs and 4 bonds. It has the tetrahedral arrangement. And that's what gives it sort of that zigzag shape that happens as it goes through here. So what we see here is sort of the expanded structural formula. This is a version of the condensed formula without the lines in between. And again, this would be more of a line structure here. Any questions on that there? As I mentioned before, sometimes we do get sort of a branch chain. And so this would be considered a branch chain. So the main part of the molecule is the guys that run the longest continuous carbon chain. And this is sort of a branch off of it. So in condensed structure, we sometimes will signify that branch and not just write it in the middle of everything like this. Again, we typically don't want to do this because this implies that this carbon's attached to all these carbons in a row, and that's really not what's happening. So sometimes when we do have that branch, we do want to make sure that we kind of do it like that. Again, if you were to do something like line structure, it would actually look something like this here. Again, this would be 1 carbon, 1 carbon, 2 carbons, 2 carbons, 3 carbons, 3 carbons, 4 carbons, 4 carbons, and the carbon that's going straight up is what would be at the end of this line here. So again, sometimes we could use line structure to represent that. Any questions on that there? Now, sometimes as well, as we will see, sometimes you may have a long, this is not super long, but will come across some where there's just a long repeating chain of carbons and hydrogens together. So for example, here, if I had something like this, CH3, CH2, 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 nobody wants to write this all day, right? And so sometimes people will shorten this up and go, okay, there's 1, 2, 3, 4, 5, 6 CH2 units in a row. So we could kind of do a shorthand here where we just got CH2 and a little 6 on the bottom to indicate that there is basically a run of 6 of those units all in a row. So sometimes it's sort of a shorthand way that we could write some of those things. Also here at the end, sometimes people will kind of do that as well. Most people will probably draw it out more like this, but again, you may see it kind of written in this fashion as well. So the skeletal structure is another way. Sometimes people call line structure. I personally call it line structure, but skeletal structure is sort of the same idea here. And again, as I mentioned, pretty much wherever a line ends, if there's nothing written there, it's assumed to be a carbon. If two lines come together, that's assumed to be a carbon. And again, the idea here is the important part about carbon is what I said earlier, the idea that there are 4 bonds to carbon, and carbon really will continuously try to continue to make 4 bonds. So the easy thing to remember is whatever is left over will be hydrogens. So whatever number of hydrogens you need to get each of those carbons to 4 is essentially what you will have going there. This is a cycloalkane here. It's got basically 6 carbons together in a ring type structure, a closed type structure. And again, this is a cyclohexane. Hexane because it has 1, 2, 3, 4, 5, 6 carbons. Cyclo because it's a ring structure. And again, in a line structure over here, this guy on the right represents what's on the left there. So again, 1 carbon here, 2 carbons here, 3 carbons, 4 carbons, 5 carbons, 6 carbons. And again, each of them, if you look at it, pretty much has 2 lines coming in, which means that each of those carbons, there should be 2 hydrogens basically there as well. And that gives us our 2, 4, 6, 8, 10, 12 hydrogens that are attached in this particular case. This is also another one here. Again, this is a cycloalkane. This is cyclopentanol. It's actually an alcohol because it has this functional group here. And you can see as we transfer it to line structure, again, 1, 2, 3, 4, 5. 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. And again, our OH group there that's in the box is represented here. So definitely if you see something written in a line structure and there's nothing at the end of it, it is a carbon. If they wanted something to be at the end of it, they will write it in like they do here. And again, as I said, what makes all these things sort of different, sort of organic molecules, the important part is that what is known as that functional group. So as I mentioned before, the functional group is really that part of a organic molecule which allows it to be identified as a certain type of organic molecule. And that's what you really want to make sure you look at when you look at organic molecules is do you need to be able to identify, okay, that is the functional group for an alcohol. So I'm dealing with an alcohol, or that's the functional group for aldehyde. I'm dealing with an aldehyde in this case. So it's really important to do that because it will allow you to sort of correctly identify what type of organic molecule you're dealing with. And also it's important in terms of the way you name things is based on the functional group. And also a lot of the reactions that occur are based on sort of the functional group that is present. So sometimes just in generic speaking, we sometimes have R and then it's attached to the functional group. Sometimes in organic chemistry, this R just represents a carbon chain. So it could be one carbon, could be a bunch of carbons attached, and then there's usually a functional group attached. So for example, sometimes ROH is like a generic way of saying an alcohol. And that's because of this OH group here is the functional group. R is basically a carbon or 2 carbons or 5 carbons or 7,000 carbons, however many carbons there are. Again, sometimes R is used to represent a carbon chain. So let's start with hydrocarbons. Hydrocarbons, pretty much like the name sounds like, are compounds that basically contain carbon and hydrogen. So the way the attachment is as we were talking about, it is carbons attached to carbons, and the hydrogens basically attach to the carbons that are here. And there's kind of 3 or 4 main classes of hydrocarbons. The first one are alkanes, and alkanes, as I mentioned, their functional group is the carbon-carbon single bond. So they have all single bonds, carbons attached to carbons and hydrogens that are there. Those are alkanes. They have a general formula of CnH2n plus 2. So what that means is, for example, if I have one carbon, n would equal 1. 2 times 1 is 2 plus 2 is 4. I should have 4 hydrogens, and that is what is known as methane. If I had 2 carbons, 2 times 2 is 4 plus 2 is 6 hydrogens, and that is what is known as ethane. So that's the general formula for an alkane. However many carbons you have, take 2 times it and then add 2 more, and that'll tell you how many hydrogens you should have. Alkenes are carbon-carbon double bonds. So somewhere in there has to be a carbon-carbon double bond for it to be an alkene. It has a general formula of CnH2n. Now, if we take, say, our 2 carbons like we had there, C2H4, that is not ethane, that is ethene, E-N-E. So ethane looks like this. I squeeze it in there. Ethene looks like, get rid of this here. Ethene looks like this, and it's got a carbon-carbon double bond. And you'll also notice a couple of things. The ethane over here, ANE, has 6 hydrogens, but to make that double bond, we had to lose 1 hydrogen and 2 hydrogens to make that double bond. So that's why we only have 4 hydrogens in ethene. Alkynes are carbon-carbon triple bonds. So the carbon-carbon triple bond is the functional group. And it has a formula of CnH2n minus 2. So we'll take our same 2 carbons. 2 carbons here would be 2 times 2 is 4. Minus 2 would be 2. So if we drew that there, it would be a double triple bond carbon with 1 hydrogen on each. And what you see is as we go through on the next bond to make that triple bond, we had to lose a couple of hydrogens to do so. Otherwise, we would have too many bonds here. And this is what is known as ethyne, Y-N-E. You can again see sort of the naming: alkane, ethane, A-N-E, alkene, E-N-E, ethene, and alkyne, Y-N-E at the end of it. The name really doesn't change that much, just the last part of it to indicate the functional group that's present. An aromatic hydrocarbon is one that contains benzene, and benzene looks like this. It has a 6 carbon ring structure with 3 double bonds. Could look like that. Double bonds could be on this side. Or a lot of times people, because those double bonds can move around, will just draw benzene with this little circle kind of in the middle to indicate it could be any one of these 2 things. That's again a resonance structure. So these are 3 ways that sometimes benzene is drawn here. So if you see something that has that ring attached to it, it is classified as a group of organic molecules known as, like I said, benzene. So let's take a look at some of these different functional groups. And again, we're going to hit pretty much all these along the way here. And we'll talk about naming all these guys. So as I mentioned before, this is our alkane with our carbon-carbon functional group, our alkene, carbon-carbon double bond, carbon-carbon triple bond. Again, our aromatic, a much nicer drawn benzene ring that is there. Some other organic functional groups that we will see along the way here. We have our alkyl halides, but we have our alcohols, which has a functional group of OH. Our ethers, which has a carbon, oxygen, carbon type of run. Our amine, which basically has a carbon and an NH2 group on it. Our thiol is a sulfur containing group, so SH. And we'll see some other ones along the way as well. But let's take a look at some parts of these. The carbonyl group, so sometimes in organic chemistry, we talk about the carbonyl group or the carbonyl carbon. That is a fancy word for the carbon-oxygen double bond. So this right here is our carbonyl group, our carbon-oxygen double bond. And it is part of a lot of different functional groups for organic molecules. That's a very important type of thing. This is a polar bond. Carbon is more positive. Oxygen is more negative here. Again, difference in electronegativity. And here's a couple of functional groups that contain that carbonyl group. An aldehyde has the functional group of carbon-oxygen double bond with a hydrogen. The ketone is 3 carbons in a row, where the middle carbon has that carbon-oxygen double bond. So again, these parts that I'm drawing here, these are again what are referred to as the functional groups. And these are the parts that when you look at an organic molecule, helps you really classify it as a certain type of organic molecule. Some more that have this sort of carbon-oxygen double bond, carboxylic acid, that has a carbon-oxygen double bond and an OH group on it. And ester has a carbon-carbon double bond and an oxygen on the back end there, again making it an ester. And again, we're going to go into more detail on all these, also known as chapters 10, 11, 12, and 13, pretty much, I think. So here's an amide. Amide is actually a nitrogen-containing group that has that. So you got this carbon-oxygen with this NH2 type group at the end of it is sort of the functional group. So again, you want to get into the habit of being able to recognize these functional groups. Again, it's going to allow you to sort of understand what you're dealing with in terms of the type of organic molecule and really how to name it properly, and also what types of reactions can happen. Any questions on that so far? And like I said, pretty much the next few chapters are pretty much going into each of these different functional groups in more detail. All right. So we will start then with alkanes, which, like I said, is the simplest sort of organic molecules you can have. Again, the functional group of alkanes is that carbon-carbon single bonds. So it can only have carbon-carbon single bonds along here. As I mentioned before, it has that general formula of CnH2n plus 2, and that's going to get you to all of your basic alkanes. Alkanes are super important for a couple of reasons. Pretty much the first 10 alkanes is pretty much what everything else is named off of. So the best thing you could do for yourself in terms of organic chemistry is to, as we will see them in just a second here, to learn the first 10 alkanes, learn their names, learn their formulas, because everything that we're going to name, everything in terms of naming, kind of formulas, structures, they all come back to these first 10. So it's super important to understand these first 10 names, have those first 10 names, not only again their names, but also their formulas as well, because everything's sort of based off of it. So when we have alkanes, they have no rings, they have that straight structure. It will have this general formula. They are sometimes called saturated alkanes. So if you have something that's saturated, what it means is it has the maximum number of hydrogens. So for example, here, if we have a run of 3 carbons, the maximum number of hydrogens that we could have would be our 8 hydrogens. And this is what is known as basically a saturated hydrocarbon, no double bonds or anything. Why would a double bond be important? Because of what we were just talking about. If I decided I wanted to put a double bond there on the first guy, what that's going to do is it is going to take away a couple of hydrogens, as you can see. So we no longer have that maximum amount of hydrogens here because of that double bond. And this is, as we will talk about in a later chapter, what is known as an unsaturated hydrocarbon. So this is unsaturated hydrocarbon. It has a double bond, doesn't have the maximum number of hydrogens. Those that do have the maximum number of hydrogens, considered a saturated hydrocarbon. Cycloalkanes are also all single bonded, but they do have the general formula very similar to an alkene, except because they have to basically close it in. So, if we had 6 hydrogens in a row, which would be hexane, and we had all these hydrogens here, our 6 carbons in a row, and all of our hydrogens here. And if we wanted to make this into sort of a ring structure, just for example, taking this carbon and slapping it together with this carbon here, we cannot do it the way it is. Again, we're going to have too many bonds to that carbon. It's not going to be able to obey the octet rule. So in order to do that, we do have to sacrifice, like I said before, a couple of hydrogens to make room. And we get this cycloalkane here. And the nice thing about cycloalkanes is pretty much you name it the same way, you just put cyclo in front of it. So this is hexane, the straight chain. It becomes cyclohexane when you put it into a ring structure. But it does have 2 less hydrogens in the straight chain. And again, we have 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons there. All alkanes, as I mentioned, will end just like the functional group name. ANE will be at the end of all these guys. So all these guys that have single bonds will end in ANE. So let's take a look at those first 10 names and structures, our formulas, which are really important. So our first one would be 1 carbon with 4 hydrogens. That is what is known as methane. Our next one would be 2 carbons and 6 hydrogens, and that is known as ethane. Next one would be 3 carbons and 8 hydrogens, which would be propane. Next one would be 4 carbons and 10 hydrogens, known as butane. 5 carbons and 12 hydrogens, known as pentane. This is just the molecular formula here. Here's our sort of condensed formula, as you can see it drawn out. Why we have this, we might as well add the rest of them here. I think it will pop up in a later chart, but we might as well put them all together. So to 6 carbons, that is known as hexane. That would be 6 carbons, and 6 times 2 is 12, plus 2 more, 14 hydrogens. Heptane is 7 carbons and would have 16 hydrogens. Octane, ANE, is 8 carbons. 8 times 2 is 16, plus 2 is 18 hydrogens. Nonane is 9 carbons and 20 hydrogens. And lastly, decane, ANE, 10 carbons and 22 hydrogens. So these 10 names here, these 10 formulas, I would learn as soon as possible, yeah, because this is very, very important to know those names, know those formulas. Like I said, everything's going to come back to these 10 guys, really, pretty much. Any questions on that there? Okay. So looking at methane here, as we talked about earlier, it has 1 carbon, 4 bonds. It has that tetrahedral arrangement because it has 4 electron pairs and 4 bonds. So it has that 109.5 tetrahedral shape. So when we start adding more than one together, this is where we start to get that sort of zigzag arrangement that occurs. Here's our ethane, which again has 2 carbons and our 6 hydrogens. Again, this would be your expanded formula. This would be your condensed over here. And again, most people put a little line between them. And this is just some models here, ball and stick models going on there. Here, when we get to our propane, again, this would be our condensed formula, expanded formula. And again, if we wanted to do our line structure here, this is what our line formula would look like. Again, each of these are a carbon, 1 carbon, 2 carbon, and 3 carbons here. And again, that is what gives it that zigzag shape, that 109.5. As soon as we keep adding a bunch of carbons, they each take that tetrahedral arrangement, and you get that sort of classic, as it's mentioned, zigzag sort of arrangement that occurs when you start putting in a bunch of carbons in a structure. Now, this is propane, and they're both the same structure here. Now, sometimes people may look at these and go, these are different, and they're really not. And this sometimes happens when we get to something known as isomers, as we'll talk about. But whenever you look at a structure and you're really trying to determine, is it the same structure? Is it a different structure? There's usually one thing that you always want to look for. You want to always look for the longest continuous carbon chain. Now, it doesn't have to be the straightest chain. It could kind of go straight, go up and over and stuff like that. The only thing you can't do is go one way and then back up and go backwards or anything like that. So going from one direction to the next, the longest continuous carbon chain. So for example, here, if we go here, that is 1, 2, and 3 carbons, nothing else attached there. This is what is known as propane based on what we just saw. Now you may look at this and go, this looks very different. Perhaps this is a different molecule. But if you look at the carbons, this is still 1, 2, and 3. Longest continuous carbon chain, still 3 carbons, nothing else attached. This is also propane. It's just drawn differently. And sometimes people think, well, they're 2 different molecules. And sometimes when people get into isomers, as we'll talk about in just a sec, they do that. They just kind of draw the bottom down or up or something like that and go, hey, it's different, but it's really not different. So one very good way you could recognize whether or not something is sort of the same or different is by looking for that longest continuous carbon chain. Now, if we look at something, say, like butane here, and we look at butane, which has our 4 carbons, and over here, this guy that has our 4 carbons. And if we count up everything, for example, this has 4 carbons and it has 10 hydrogens. So if you count up all the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. If you come down here, this guy also has 4 carbons, also has 10 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you may go, well, these are definitely the same thing. And if we look at the structure here, this is 1 carbon, 2 carbons, 3 carbons, 4 carbons in a row, nothing else attached. This is what we call butane. But if we look at the bottom one, I'll redraw it here. Maybe a little, not so much. We'll just kind of draw it like this here. I'll draw it more the condensed way. And we got that coming up here. And we have an H. So if we count the longest carbon chain on the bottom guy, it is, we have 1 carbon, 2 carbons, 3 carbons only. If we go 1 carbon, 2 carbons, 3 carbons, that's the best you could do there. If we went 1 carbon, 2 carbons, and then up to 3 carbons. So no matter which way we go, and you should always look at all the different options in terms of the ways to count, there's only 3 carbons, no matter what you do. So when you look at something like this, the longest continuous carbon chain is only 3. And 3 carbons is not butane, if you remember back here where we were talking. 3 carbons is propane. So the name of this guy would not be butane like the other guy, but the base of this guy's name would actually be propane. And that would encompass the longest continuous carbon chain here. Now, you may also say to yourself, but there's something else attached there, and you're right if we look to the top here. there is this guy attached. Now, when we start naming things, and we'll talk more about how to do this, but I'm going to give you the Cliff Note version here since we're in the midst of looking at this. When we have the longest continuous carbon chain, and you have many options like I did here on the left, always good to take the straightest and kind of put a box around it. That is really your main chain. And the main chain is really what you name, kind of the base of the name is going to be. Now, whatever else is attached, these are sometimes referred to as groups. And because this is a carbon group, this is sometimes referred to as an alkyl group, which is a fancy way of saying a carbon group, basically. And carbon groups, which are alkyl groups, they're actually named off of, surprisingly, those first 10 alkanes as well. So if we look at this group that's there, it's basically a CH3. And ultimately, this has one carbon. And if you remember back, the guy that has one carbon is known as methane, right? And methane has one carbon, but it has 4 hydrogens, right? So it's very similar, but different. And the difference here is it is missing 1 hydrogen. The reason it's missing 1 hydrogen is if this carbon up on top that's in the blue circle had 4 hydrogens, the carbon here would then have 5 bonds, too many electrons, right? So what an alkyl group is basically an alkane that's missing a hydrogen. And that missing hydrogen gives it a place to attach to the main chain and still maintain octet rule and not go over 8. And oddly, it is named the same way. This is what is known as an alkyl group, YL. So instead of methane, this is what is known as a methyl group, YL. Methyl from methane, YL, because it's a group is missing 1 hydrogen to allow it to connect. That means that we would add that to the name here, and this would be methyl propane. In addition, though, we typically give the location of where these groups are located. So if we number the main chain, this is carbon 1, for example, this is carbon 2, say that's carbon 3. This would be 2-methyl propane, 2 because the methyl group's at carbon number 2, methyl because it's a methyl group, and the biggest chain is 3 carbons in a row, which is propane. That's sort of a Cliff Note version of naming. We're going to talk obviously how to do that in just a bit here. But that's sort of how we get this name. And one thing you'll also see in organic chemistry is what you see down here. They also call it isobutane because organic molecules have like 9,000 different names. It has the systematic name, has the common name, has the historical name. You know, there's a lot of different types of names. But this is also called 2-methyl propane. So because this actually has a different name, it has really a different connection, the guy on the bottom to the guy on top. These are actually 2 different compounds that have the same molecular formula. And whenever you have something that has the same molecular formula, but has a different connection and is a different compound, these are what are known as isomers. So isomers are organic guys that have the exact same molecular formula as we see here. They both have 4 carbons. They both have 10 hydrogens, but they have a different connection, and that different connection gives them different names and also gives them different properties. Any questions on that there? Okay. So here's another example of a couple of isomers. Again, isomers, exact same molecular formula, different connectivity, and different names. And that really is the best way to know if you actually did draw an isomer or not an isomer, is try to name them both. And if you end up with the same name, you didn't draw an isomer. If you end up with 2 different names and you did it correctly, you probably drew 2 isomers. So that's a very common sort of thing. Here again, if we just do some math on these guys on the bottom, we got 2 carbons in each. We got 6 hydrogens on each side, also 1 oxygen on each side. But because of the way they are connected, this has a functional group of OH, which is an alcohol. This has the functional group of carbon, oxygen, carbon, which is an ether. So these are 2 different types of organic compounds. They have the exact same molecular formula, And again, they are known as isomers. And they're also known as constitutional isomers. These are, again, guys that are connected differently, but have, again, the exact same numbers of elements. They also have very different properties, the alcohol versus the ether. And again, they're actually named very differently as well. So as you can see, one is called ethanol and one is called dimethyl ether. Again, you can see what I was saying before. This has actually two carbons. Two carbons is ethane, and you can see it is still based off of that name, OL, because it's an alcohol. So ethanol, OL, because of the alcohol part. And again, the two carbons is from ethane. So again, very important when you draw isomers that, you do end up with something different. Here's another example here of pentane. 5 carbons in a row. So this has got 5 carbons. It also has 12 hydrogens. This guy over here also has 5 carbons and 12 hydrogens. Same thing here. These are all isomers of each other. And again, sometimes when people would try to draw, say, pentane as an isomer, they'll do something like this. And they'll draw something, say, like this. And go, well, this is definitely an isomer. See, it's going down. But if we follow our rules for counting the longest continuous carbon chain, 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons all in a row, it's continuous. This is still pentane. Even though you drew it down, it is still pentane. It is not an isomer. Why are the other ones isomers? Well, let's look at them and talk about naming these guys and see how we get to these names, and kind of be a preview of what we're going to be talking about. If we go for the longest carbon chain here on the center guy, we have 1 carbon, 2 carbons, 3 carbons, and 4 carbons. We could also go 1 carbon, 2 carbons, 3 carbons, so that's less. We could go 1 carbon, 2 carbons, 3 carbons, and 4 carbons. That's the same. So no matter which way we go, it's 4 carbons is our longest continuous carbon chain. Again, I recommend that if you have the same number in multiple directions, that you take the smallest or the straightest one and use that as your longest chain. So I'm just going to take the straightest one because that's easiest. And again, the straightest one is 4 carbons. 4 carbons, the base of the name is going to be butane, because it has 4 carbons. Again, here, attached off of it is a carbon containing group. This, like we saw before, has 1 carbon attached. So it's not part of the main chain. So it's going to be based off of methane. This is a methyl group, YL, which is where the name here comes from. Now we need to give the location of where that group is located. And when you go to give the location, and that really is what all of organic naming is about, it's about location, location, location. So when we do this, we want to number the carbons in the longest chain, which is in our box here. So if I numbered left to right, this would be carbon 1, this would be carbon 2, this would be carbon 3, and this would be carbon 4. If I numbered right to left, which would be my other option there, this would be carbon 1, this would be carbon 2, this would be carbon 3, and this would be carbon 4. When we name things in organic chemistry and when we're trying to choose which way we should number the main chain, we should always number whichever way gives the group the smaller number. So in this particular case, going in the blue direction here, we'll give that methyl group the smaller number of 2. If I went in the purple direction, right to left, it would have a number of 3 for the carbon. So that's why we end up with 2-methyl butane, a different name than pentane. These are 2 different guys, and these are isomers of each other. Any questions on that name there? Now, if we do the same thing here on the last guy, longest continuous carbon chain, 1 carbon, 2 carbons, 3 carbons. You can also get 3 carbons if you go this way, and this way. You can also get 3 carbons if you just go straight on up. And it really doesn't matter which way you go, because technically speaking, no matter which way you go, if they're the same numbers, you'll end up with the same name. It really doesn't matter. But in this particular case here, again, I'm just going to go with the straightest. So the straightest, longest continuous carbon chain is right about there. And that is 3 carbons. Going back to our list of first 10 alkanes, 3 carbons is propane. That is where the base of our name comes from. In this particular case, we have a group that's up here. That's a 1 carbon group. That is still a methyl group. We also have another 1 carbon group on the bottom end here. That is also a methyl group. That is 2 methyl groups in the same compound. So we add a prefix for that. And that's why we have it known as dimethyl. It doesn't matter if they're on the same carbon or not. In this particular case, it just means that there are 2 of those groups in the compound. They don't have to be on the same carbon. Lastly, here we want to number the longest continuous chain to give those groups the smallest number. And in this particular case, it doesn't matter if you go left to right, it's 1, 2, 3. If you go right to left, it's 1, 2, 3. No matter which way you go, those groups have the number 2. But the important part is here, what do we see is 1 carbon group there, 1 carbon group there. We actually do have to give both numbers. 1 number for each of the methyl groups that are attached. As weird as it may sound, that is 2,2-dimethyl propane. And again, that is a different name than this guy and a different name than this guy. All 3 of these guys are isomers of each other. They all have different properties because of the way they're connected. And the way you could identify it is they all 3 have different names. That's a super good way to recognize whether or not you actually drew an isomer or not. A couple other things that you may notice here in sort of this naming is we always use between a number and a letter a dash. So dash between a number and a letter. And if you have 2 numbers like we do on that last one, there's a comma between 2 numbers. As I kind of erased it badly there. Let's try and do that a little better. There. A comma between 2 numbers is what we do here. So between 2 numbers, comma, between a number and a letter, a dash goes in the name. Again here, number and letter, we put a dash. And again, between 2 numbers, a comma, and number and a letter, a dash. Any question on those there? Here's the rest of the 10 alkanes, which, as I mentioned before, really important to make sure that you have these first 10 down in terms of name and formula. Everything, as you can sort of see here, does come back to that. So let's talk about how we really go about naming these. Sort of what I did there is how we go about naming them. But let's do some here just to make sure. A couple of things. We usually name things in terms of the IUPAC name. You hear that a lot in organic chemistry. That stands for the International Union of Pure and Applied Chemistry. Those are the nice 3 guys that name everything, come up with the names on the periodic table, and all those weird, funky rules, as we will see as we go through here. But pretty much for our class on most things, and in most cases, you should go for the IUPAC name. It's kind of like the official name, if you will, in terms of naming things, and that's the way you should sort of kind of go by it. We will see things as we go through these different chapters that do have, like I said, common names, historical type names that people still use and does pop up very often. But basically the basis of the name, as we kind of went through those few examples there, is basically you always want to look for that longest continuous carbon chain. And again, it does not have to be the straightest. It can go this way, then come up, and then go over. The only thing you cannot do is go from one side to the next and back up and go backward. So you have to sort of start at one end until you hit a dead end, and then you stop. And then you start at a different starting place and hit another dead end. Again, no back and forth in terms of counting. Whatever that continuous longest carbon chain will be, will match one of those 10 alkane names, and that will be the base of your name. as we did before, everything that is not part of the longest continuous carbon chain will be considered a group. And a lot of times those group are those alkyl groups, which are pretty much those 10 alkanes without a hydrogen, one hydrogen missing, so that it has a way to attach. And like I said, pretty much all naming is all about location, location, location. You're basically telling everybody exactly where you could find everything in the particular molecule. As I mentioned before, alkyl groups will get a YL at the end of it. Again, also based off of the alkane name, like our methane became a methyl group. If we had a ethyl group, it comes from ethane. If we had a propane type group here, missing one hydrogen to allow it to connect, this would be a propyl group. Now, when we look at carbons, by the way, carbons can be classified as a primary carbon, a secondary carbon, or a tertiary carbon. Now, when you have basically a carbon that is attached to one other carbon, that is a primary carbon. When you have a carbon that is attached to, oddly, two other carbons, that is a secondary carbon. And when you have a carbon that is attached to three other carbons, the guy in the circle is attached to three other carbons, that is a tertiary carbon. So you can identify carbons as primary, secondary, or tertiary. This carbon here is a primary carbon. That's where we lose the hydrogen. This carbon here was a primary carbon. That's where we lose the hydrogen. But sometimes the hydrogen that comes off is not the primary carbon. So perhaps if we took our propane, which is this guy, and again, this carbon here is a primary carbon. So if we lost any of the hydrogens on that, we will end up with this guy. This guy over here is a primary carbon. So if we lost any of the hydrogens on that guy, we would also end up with this guy. This carbon in the middle is a secondary carbon. It's attached to two other carbons. If we lose the hydrogen on that guy, we actually get a different type of group, because the connection is not going to be at the end carbon where it would attach to the actual chain. It would attach right here at our secondary carbon. It would attach in. And this guy here actually has a special name. This is what is known as isopropyl. This is the isopropyl group. And it has this arrangement of CH3, CH, CH3, sort of the condensed way you sometimes will see it written. And that has a special name, which is known as the isopropyl group. So there actually are some groups that have special names, and it's based off of what carbon loses the hydrogen that allows it to connect. So because this actually connects through the secondary carbon, it actually has a different name, that group, than this guy over here on the left. This guy is sometimes called an N-propyl or normal propyl group, because this comes off of the primary carbon here where it attaches. So sometimes you'll see groups like sec-butyl, SEC butyl group, and that means that's a secondary carbon. That's where it's attaching. Tert-butyl, T-butyl, that is the tertiary carbon where it's attaching. So sometimes these groups do affect the name based on the carbon that's being attaching here. These are just sort of normal arrangements where it just attaches to the end carbon. These are all primary carbons where they're attached. And again, when we lose one of those hydrogens, we get our methyl group, our ethyl group, propyl group, butyl group, pentyl group, hexyl group, and obviously you can continue on in that particular case. Here's another table, and again, here's what I was talking about. Here's our isopropyl group. It is the secondary carbon that's attaching. Our isobutyl group is the primary guy. Our sec-butyl is the secondary carbon that's attaching. Our tertiary butyl or T-butyl group this is our tertiary carbon attached to 1, 2, and 3 carbons that are there. For our purposes, this is the one you usually will come across in this class the most, probably the isopropyl group. You'll see that happen the most. Any questions on that there? All right, let's get into some naming here. All right, let's just talk about how to get to this name here. So first off, if we have this guy drawn, which by the way, 1, 2, 3, 4, 5, 6 here, it would look. In case you're curious what the line structure would look like, very badly drawn one. I missed the corner there, but it'll look something like this. Again, we want to take our longest continuous carbon chain. So 1, 2, 3, 4, 5, 6 carbons. Again, you could get that in multiple ways. You could go 1, 2, 3, 4, 5, and 6. Again, if you have multiple ways that end up being the same in terms of the number, just go with the straightest one. It's usually the easiest to do. And as you can see there, just put a box around it. So 6 carbons in a row is going to be based off of hexane. Again, here we do have one group that's attached. That's our alkyl group. It has 1 carbon. That is a methyl group. So what is left is we need to give the location of that methyl group. So there's 2 ways you can number this carbons. This would be carbon 1, this would be carbon 2, this would be carbon 3, 4, 5, and 6. Or you could go the opposite way, starting on the right. 1, 2, 3, 4, 5, and 6. We always want to give the group the smallest number. So the proper way to number this is going left to right here. That means that our methyl group is sitting at carbon number 2 of the main chain, and putting all that together would give us for this guy 2-methyl, again, a dash between the number and the letter, and hexane. So 2-methyl hexane would be this guy in line structure and the guy that's on the bottom. Any questions on that name? And just in case you're curious, in line structure, people oftentimes are curious. They're like, hey, this line has nothing at the end of it. Again, it's a carbon that should have 3 hydrogens. So it is this methyl group that's at the end of it. So very common, people will see a line structure drawn with just a line and go, I'm not sure what's at the end of it. Any questions on how I got to that name there? Now here, as I mentioned, it does not have to necessarily be the straightest. So here we have our 6 that goes straight across. We also could go 1, 2, 3, 4, 5, 6. Again, goes down and over, still longest continuous. I did not back up or go back around. Could even start up high, go down, come back, and go back up as well. So sometimes you want to make sure you check all of your options in terms of longest continuous carbon chain will not always just be the straightest. The deal is, as I mentioned, you just can't, like backtrack and head back the other way or anything like that. So you got to go one way and then hit a dead end and stop. All right, so we did that. We got to that name. Blah, blah, blah. Again, a couple other things, as I mentioned, if you do have more than one group in a particular compound, even if it's not on the same carbon, you do need to add di, tri, tetra, or something like that as well. So here, if we look at this guy here, let's take a look. We got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons. If we started here and went this way, that's 5 carbons. If we started here, 1, 2, 3, 4, 5, and 6. So we get 6 going that way as well. So it looks like 6 is the winner, but we do want to just take the straightest because it's easier to deal with. So again, here on this guy, 6 carbons is going to give us the base of hexane as well. We do have a CH3 group here and a CH3 group here. So because there's 2 methyl groups in this compound, that's how we get to the dimethyl part. And now we need to give locations. So if we go about numbering left to right, this is carbon 1, 2, 3. This would be carbon 4, carbon 5, and carbon 6. So we would have groups at carbons 2 and 3 going left to right. If we numbered right to left, which is your other option in this case, this would be carbon 1, this would be carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Going sort of the purple direction, we would have groups at carbons 4 and 5. And it is as simple as 2 and 3 is a smaller number than 4 and 5. So we would want to go left to right here in terms of the numbering. And that means that we would want to use both of those numbers in there. And this would be 2, 3, again, parentheses, not parentheses, comma between 2 and 3, the 2 numbers, and then a dash here between the number and the letter. So this would be 2,3 dimethyl hexane. Any questions on that? Now, when we have groups, in this particular case, we had 2 groups that were the same. But if we do have groups that are not the same, we do put the groups together in alphabetical order, regardless of number. So it goes alphabetical order for the groups, regardless of number, and if we have different groups that are attached. So that's what that should say next. All right. So that one we named, that one we got to, that was the one we did earlier. That's good, they agree. Hopefully they agree on this name as well. Let's hope. There you go. So let's take a look at, let's see here. All right. So again here, if we look at this guy, we want to count up our longest continuous carbon chain. There is a lot of carbons going on here. So if we just go straight off, it's a good idea to start. 1, 2, 3, 4, 5, 6, 7, and 8 carbons. We could go 1, 2, 3, 4, 5, and go up 6 and 7 carbons. That's less. We could go on the right here, 1, 2, 3, 4, 5, and 6 carbons. So that's less. And we could go right 1, 2, 3, 4, 5, 6, 7, and 8. So it looks like we have a couple of ways we could actually get to 8. Again, here we would probably just want to take the straightest way here to get to 8. So that straightest way to get to 8 is going to be our longest carbon chain. 8 carbons in a row based off of our first 10 alkanes is going to be our octane. We now have a methyl group here. We also have a methyl group over here. And we also have another group that's here as well. We have a ethyl group, right? And that is 2 carbons. 2 carbons based off of ethane. Drop the ANE, put the YL there, and that would be ethyl. So when we go to name this guy, we need to number. Now going left to right, this is carbon 1. This would be carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, carbon 8. Now, counting up everything we got going in terms of location, we would have a group at carbon 2, we would have a group at carbon 5, and we would have a group at carbon 6 going left to right. Now, if we went right to left and numbered, this would be carbon 1, this would be carbon 2, this would be carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, and carbon 8. Going in sort of the blue direction here, we would have somebody at carbon 3, somebody at carbon 4, and somebody at carbon 7. It is the same rule here. 2 is less than 3, so we would not want to go this way. So we would want to number the red way here. And now we got a couple of things happening here. We do have 2 methyl groups in there, so that is dimethyl in terms of that group. We also have a ethyl group. And again, in alphabetical order, it is the ethyl that comes first. E before M. We ignore prefix here. So we are going to go E before M. And this would be 5-ethyl. Location of where the ethyl group is right here, carbon number 5. And we also then have 2 numbers, and that was 2 and 5, I believe. 2 and 6, I'm sorry. 2 and 6. Dimethyl octane, putting all that together. So 5-ethyl, 2,6-dimethyl octane. Again here, alphabetical, regardless of prefix, regardless of number. It goes alphabetical, E before M here in terms of that. And again, dashes between numbers and letters, and commas between 2 numbers. Any questions on that? Okay. So since we're getting to the end and we talked about sort of naming it from the structure, I want to quickly here before we wrap it up for today, talk about how to draw a structure from the name. So let's just say we had, I don't know, 3-methyl. Let's go with 3-methyl hexane. Okay. Whenever you're given the name and you want to draw it, it's always a good idea to start from the back of the name and work this way. So what I mean by that is when I see hexane, what I should lay up is really 6 carbons in a row, nothing else. Just draw 6 carbons in a row. That's 6, I hope. That pretty much takes care of this part of the name, the hexane part. 3-methyl means I have a methyl group at carbon number 3. The nice thing about you drawing it is you can go left to right, or you could go right to left. I'm going to go right to left and call this guy carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. You could go whichever way you want. You could go the opposite way. That means on my drawing here, carbon number 3, I should put a methyl group, which is a CH3 group. That takes care of that. Everything else that you need to draw should be hydrogens. And pretty much you need to make sure the magic number for carbon is 4. So you need to make sure you put enough hydrogens that each carbon has 4 bonds. This guy at the end has 1 bond. He needs 3 hydrogens. This carbon next to him has 2 bonds coming in. He needs 2 hydrogens. Carbon next to that also needs 2 hydrogens. This carbon here has 3 bonds. He needs just 1 hydrogen. Carbon next to it has 2 bonds, needs 2 hydrogens. Carbon at the end needs 3. Drawing it from the name is actually the easiest, I think. You just work backwards. Start with just the carbons, put on all the groups to the correct numbers, and then fill up everything else with hydrogens until all the carbons have 4 bonds. The important part is whichever way you decide numbering. So I decided to go 1 through 6 this way. You have to stick with it for everybody else. So whichever way you choose, you've got to stick with that numbering for all the groups that you're attaching. But then everything else will just be hydrogens. Any questions on that there? Okay, so we will pick up with this, probably roll into chapter 11 on Wednesday as well. If you didn't put here, make sure you do so. If you're off to lab, have a good lab. And I'll see everybody in discussion in about 5 minutes or so.